Hello, everybody. Now that you have learned what the limit of a function is, we are going to study some theorems, rules, formulas about how those limits work. For instance, when you have two limits, can you add them, subtract them? Can you multiply them? And there are all sorts of theorems. The good news is those are pretty simple and very clearly understood. So we are going to go right into 2.3, theorems and rules and formulas about limits. Let's get started in section 2.3. All right, so we have the well-known theorems concerning limits. Now, the word theorem, I should make a little comment first about this word. There is a similar word, that's theory, right? So you can talk about the scientific theory of this and that. And so a theory is a sort of a body of knowledge that is well accepted in the discipline. That would be like the theory. Now we have mathematical theories as well. The theory of abstract algebra, the theory of geometry, and so on. And those sort of like field specific things, the knowledge or the questions and theorems and examples and counterexamples within that specific field of mathematics. That would be a mathematical theory. The word theorem is actually different from a theory, right? And the word theorem comes from a Greek word that means to look carefully or to behold. And so these in our language mean accepted, proved statements. So these are proved true. How do we know in mathematics something is true? Well, we prove things, okay? And so because these are proved, these are going to be always and forever going to be true, right? And correct. And so there is a proof for everything I'm going to mention in this section. However, those proofs are rather difficult because remember when we learned about the limits, I did not give you a precisely mathematical definition of what a limit is. I instead gave you an intuitive understanding or definition of limits. I said, I called that a working definition of the limit of a function. And so once you understand or once you get the precise definition of a limit, you can precisely prove these things. Thanks to the generations of mathematicians, these have been proved using precise definitions. But we will, of course, not talk about those or look at those. That is something that you will be studying if you go into a four-year university to a class like real analysis, maybe advanced calculus or something like that, okay? So you can wait until that time to study the proofs of these theorems, which we are about to study. All right, so now, without further ado, let's talk about the theorems and ideas related to limits. We are going to list a lot of them. So let me just give you the first, the settings. Okay, so let's say the limit of f as x approaches a is L, and you have another function, g. Okay, and by the way, these are the theorems that we will be using to do to find lots of limits of many different functions in the probably the next segment of this lecture video. Limit of g as x approaches a is m. Okay, so let's say these are given. Then, okay, so let's start listing these. Okay, basically everything I'm going to say will be intuitive. What you think the answer should be will turn out to be the answer. Okay, so what happens if you add two functions like f plus g? Remember, you can add two functions. You know, an algebra of the set of functions will allow us to add two functions. If you add these two functions, f and g, what's going to happen to the limit? Well, not surprisingly, it'll just be the sum of these two limits. Okay, so the limit of f of g, f plus g at a will be the limit of f at a plus the limit of g at a. What happens if you do subtraction? Okay, f minus g is a new function. That too is going to behave nicely. The limit will be the difference of those two limits. What happens if you multiply, remember you can multiply two functions. F times g will be fx times gx. Then you can find the limit by multiplying those two limits together. Again, nothing not surprisingly. Now, what happens if you divide f by g? You get a new function, and the limit is also L divided by m. Of course, here we have to assume that m is not equal to 0, because if m is equal to 0, then the function would be undefined, right? Or the limit will be undefined. All right. What happens if you take the limit of one of these functions, let's say f, and then you raise it to the power of n? Okay. Again, not surprisingly, the answer is going to be the limit raised to the nth power. Okay. So far, no surprise. And in fact, there will not be any surprise in this. Okay. So what happens if you take the square root of the function f of x? Okay. Well, then the answer is going to be the square root of the limit. Okay. Provided that limit is greater than or equal to 0. Okay. And of course, that is something we have to assume. And so everything that I said, let's put one more thing here. What happens to the limit if you take the log, natural log, let's say, or common log of fx? Okay. Well, then the answer is going to be the log of the limit. Okay. Again, assuming that L is positive. Okay. So all of these would just be true, naturally. I'm going to just pause this, and I'm going to add some English writings on here so that you can remember these easily. All right, so many times I said this, that sometimes, reading mathematics, it may be hard because that's written in like what appears to be a foreign language. Okay, so for instance, here's my, here's your class notes. I hope you're taking notes as you watch these lectures on video. But if you show this to your friends who are not familiar with mathematics, they will, just look at these notes and say, I have no idea what this says, right? So sometimes interpreting these in English, in your native language, is going to help, all right? So let's say, what does one say? One basically, parentheses 1, says that the limit of a sum is the sum of the limits. Okay, so the limit of a sum, that's the left-hand side, is the sum of the two limits, L plus M, right? Okay, and what does number 2 say? How do you translate number 2 into the English language? The limit of a difference is the difference of the limits. Okay, no problem here, right? How about the third? I guess you get the idea by now, right? The limit of a product, that's FG, is the product of the two limits. That's ML times M. Okay, number 4. The quotient of, the limit of a quotient is the quotient of the limits if the denominator is not 0. All right, number 5 says the nth power, the limit of the nth power is, let's say, of a function is the nth power of the limit. And that means, of course, L to the nth power. And let's do one more, maybe 2 more. We'll have 2 more here. Yep. Okay. So maybe I can just do this one here. Okay, number 6. There's the root, the limit of the square root of a function is the square root of the limit. You see why I'm writing this, right? Because I didn't want to handwrite all of these. And you don't have to write these either. But I think it's a good thing to try to say or explain these things in English. All right, so that's why I'm trying to help you out. So number 6 says the limit of the root is the the root of the limit, right? And then finally, number 7, the log of, no, the limit of a log. Limit of the log of a function is, and by the way, it doesn't matter what the base is. I am using here the natural log with base e, but it does not have to be e as the base. You can have the common log or log base 2 or log base 17 if you like. The limit of the log of a function is the log of the limit of the function, right? So that is, so limit of the log is a log of a limit. So you kind of switch things around, and all of these should make sense. Now, what do we do with this? Yeah, there's one more actually. And so the answer, what do you do with these, is that you can actually find a bunch of limits using these theorems. And sometimes you don't even know that you're using these theorems because they are so intuitive, and you almost take these for granted. But that's okay, as long as you can find the limits. And we will exercise, we will do some exercises, examples, and demonstrations to show you what kind of techniques we have to find limits. Remember, x doesn't ever get to exactly a. X gets closer and closer to a. Another word, a and x are clearly different. X minus a cannot be 0. That's something very important for you to remember. All right, so I'm going to use a different color here just to tell you something that's very practical. Remember, for continuous functions, continuous means that there's no hole, no function going to infinity, or no gap or anything. For continuous functions, which we will study more precisely in the next section, I think 2.4. For continuous functions, guess what? The limit is the same as the value of the function, right? So for continuous functions, just plug in the number, and the value of the function can be evaluated, and that is going to be the limit. Okay, so that's not hard. For others, so these are practical sort of tips for finding limits. For other functions, okay, when you cannot plug in, or when you plug in, you get things like 0 over 0, or things that don't make sense, or whatever. For other functions, try canceling. Maybe you can factor. Maybe using conjugates. Now, I will tell you what conjugates are, and I think you'll remember many of the things that you learned in algebra classes are going to be used in order to find these limits. And that's why you had to, learn these algebra and take algebra classes. Okay, so etc. All right, let's do some practice problems here. I have many examples in this case, so I'm going to write out the word examples. E.g. is okay. All right, so number 1, let's find the limit of 3x minus 2 as x approaches 1. Oh, let's do 10. Okay. Now, what kind of a function is 3x minus 2? Well, that's a polynomial function. It's continuous. You can just plug it in. Now, why can you plug it in? Well, that's because of all these theorems. Remember theorem here, the 1 and 2 and 3. Basically, it says that, oh, by the way, you can also take out a constant. I guess I didn't say that. Maybe I should say that here. All right. This is also kind of intuitive, and I probably should have mentioned this. If you have a constant times a function, then the constant can be taken out, all right? And so that's something I probably should have said earlier, but this can be removed and placed on the front if k is constant. So I apologize for adding this in last minute, but that's what you need to have here. You don't actually have to have it because the constant itself is a function, and you can use that as your f or g or whatever. Okay, so this, technically speaking, if you are using these, the theorems that we just learned, you can write this as the limit of 3x minus the limit of 2. And of course, the limit of a constant is a constant. And 3 can be moved up in front. So this will be 3 times the limit of x, all that. But you don't really have to do show step by step like that. All you have to do is to plug this in. Plug in 10 for 3, and that's 30 minus 2, that's 28. Okay, so if you have a polynomial or anything that you can plug in to find the solution, that would be the solution in most of these cases, unless you have a 0 denominator or something like that. Okay, what happens if you have x squared plus 2x over x as x approaches 0? Now you can't plug this in, right? You can plug, well, if you try to plug in 0 for x, you have a 0 over 0, which I told you is a vulgar term, offensive term, foul language. And so you don't want to even write that, okay? So you have to do something. Remember, x gets close to 0, but x is never 0, right? So you can cancel if you see x on the top and the bottom. So for instance, you can factor this, okay? You see that the common factor here, and I can cross these out because, you know, I know that x is never equal to 0. Well, that's x plus 2. Oh, by the way, I apologize. I really should not be writing this. Limit is not equal to this. Okay, so I apologize. What I should have written is that this is the limit as x approaches 0 of that, which is the same thing as the limit as x approaches 0 of x plus 2. Now you can plug in 0, and the answer is 2. Okay, now I want to be mindful of, you know, the mathematical precision. I'm a math instructor, I'm a math professor, I am a mathematician, so I will feel very uncomfortable if I didn't have this LIM like this, because this is the limit we are trying to find. This is clearly different from that expression, which is just an algebraic expression. So that's why I want to make sure that I write things correctly, okay? And I expect you to follow and maintain that level of precision as well. So, you know, again, I know this is a lot to ask, but you should learn to practice writing precisely correct mathematics. All right, let's look at the third example. Now, this is going to be a little more difficult one. Let's see if you can figure this out. X squared minus 3x divided by 2x squared minus 5x minus 3 as x approaches 3. Okay, so what kind of a function is this? That would be usually the first question you want to ask yourself. And the answer is it's a polynomial over a polynomial, and therefore it is a rational function, right? And if you try to plug in 3, you get, okay, I'm going to erase this as soon as I write this, so don't write this down. But if I try to plug in 3 here, you get 3 squared minus 3 times 3 over 2 times 9 minus 15 minus 3. Okay, I hope you agree this is 0 over 0. Now, remember, I said I'm not going to keep this because, again, 0 over 0 is something I would be embarrassed to write in front of people, and so I have just erased it. Okay, so what can you do? Remember, x is never equal to 3, so the denominator is never 0. One of the common things you could do is factoring. If you have a polynomial, try to factor. This is x minus 3, right? Now the denominator, well, you can do this kind of a factoring, 2x and x. To get 3, maybe you have to have 1 and 3. 1 and 3 here, you have 6 and 1 for the outside and the inside product. Somehow I think I can create -5, right? So it's minus here and plus here. Let's make sure. If you multiply these together, you get 2x squared minus 6x plus x, that's -5x. And then this times this is -3. Okay, so I have factored this correctly. It's important to do it correctly. And then you can see, oh yeah, oh, yes, I can cancel this and this. And now, see, the thing is, why couldn't you plug in x is equal to 3 in the first place? That's because you had this factor x minus 3 and x minus 3, and that's why you got 0 over 0. So in a sense, x minus 3 was the bad factor. It was the bad guy, okay? And you saw the bad guy on top and the bottom, and they end up, sort of disappearing, right? Because we canceled them, cancel culture. All right, so then you have x on the top, 2x plus 1. Ooh, look at that now. Now you can plug in 3. So it's 3 over 6 plus 1, 7, right? And that's the answer to this question. You couldn't plug in directly, but just with a little work, you actually got the answer. By the way, you don't have to put the LIM right here, because now this is the answer. The limit is precisely equal to 3 over 7. All right. For the next one, okay, well, let's go ahead. I guess I don't have to worry about this page break. All right, so this time I'm going to give you this question. Limit of the square root of x minus 1 minus 2 all over x minus 5 as x approaches 5. All right, try to plug in 5. Oh, this is not even a rational function because the top is not a polynomial. I hope you understand that. As soon as you see a square root, that ceases to be a polynomial. So when you plug in 5, you get square root of 4 minus 2, that's 0. And then 5 minus 5, that's 0. Again, 0 over 0. So you can't just plug in directly. You can't even factor in this case, right? So what can you do? Well, you remember, you remember what I was talking about a few minutes ago? There is a way to sort of rationalize what you have on the top. And that is by multiplying this by what is known as the conjugate. And the conjugate of square root of x minus 1 plus 2, minus 2 is the square root of x minus 1 plus 2. You change this sign here, and that's called the conjugate or conjugate in Latin. What does conjugate in Latin mean? It means very, very symbolically, spouse, okay? So that's a wonderful word. Conjugate means the spouse. See, they are not the same, but they are similar to each other, and they're right next to each other, and when you multiply them, they become rational and stop being radical. That's what spouses do. They help each other not become radical. All right, and so, well, I can't just multiply this on the top. I have to also multiply the bottom by the same number, right? Because this whole thing is equal to 1, and I can always multiply something by 1 without changing it. Notice here, I am about to introduce a radical sign in the denominator. Okay, is that a bad thing? Yes, maybe your teacher told you it's a bad thing, but I'm telling you, it's not that bad. Okay, sometimes it's necessary to introduce a irrational or radical expression in the denominator. Now, what's going to happen to the top? Okay, so you remember it's a minus b times a plus b, right? And the answer is a squared minus b squared. So if you square these, you get x minus 1. Let's just combine these. Okay, the top is x minus 1, and then you subtract from that 2 squared, which is 4, right? So, and you say, well, I mean, this is a cleverly designed question. In the real life, how fortunate do you have to be to get a nice expression like this? And that's true. Okay, this problem was carefully designed to illustrate this point. What happens is the numerator becomes x minus 5, and the denominator also has x minus 5 in it, right? So they, at this point, cancel each other because we know that x is not exactly 5. X is close to 5, but it's not 5. So x minus 5 is not 0, and therefore we can cancel on the top and the bottom. Okay, so then the fraction becomes, remember, I still have to put LIM every time I put an equal sign. All right, so what happened? I couldn't have plugged in 5 at the beginning because x minus 5 was a factor in the denominator. Now that bad guy has been canceled. it's gone. So now we should be able to plug in 5, okay? So then this becomes 4 and plus 2. Notice here, I don't have the 0 denominator anymore. It's 2 plus 2. What is 2 plus 2? It's 4, of course, right? So the answer is 1/4. Okay, let's do one more question, and then we will go into the second part of the video for this section. All right, so this one is also a little more challenging because this time you have a sum of 2 rational expressions. You may want to pause your video at this point, okay? So we have never seen anything like this. And by the way, this limit, the limit of this, the first term is undefined. It doesn't exist. One side goes to positive infinity, the other side goes to negative infinity. This, we have no idea, right? But somehow, oh yeah, by the way, because this limit and this limit does not exist at 3, we can't use number 2 of the theorem that says the limit of the difference is the difference of limits, because each limit does not exist. But there is something you can do here. So think about that and see if you can do that when you pause this and try to come back to it. Okay, so hopefully you did what you basically had to do, right? Which is to actually compute what's inside of this, right? So you have x minus 3, and what's this denominator here? Can you factor this? Yeah, you should be able to factor this too, x minus 3 and x plus 1. So all you had to do was to factor this binomial, right? And you see that. Now you could almost guess that x minus 3 has to be one of the factors, because that's in the other denominator. Okay, so now can you do this? So you have this, and x minus 1, x plus 1 has to be multiplied on the top and the bottom of the first expression. Okay, remember this expression is the same as this expression, because all I did is to multiply the top and the bottom by x plus 1, right? Which, by the way, is something you can always do. The top and the bottom can be multiplied by the same number. All right, and then the next one, this is just minus 4. Okay, now the denominator, the new common denominator is that, so I can just express this whole thing this way. All right, so now what do you get? The top is x minus 3. Again, very cleverly designed problem, right? Because now you can see x minus 3 on the top and on the bottom. Now, what happens if you don't see x minus 3 on the top and the bottom? Then the problem is not something you can do. It may actually be an infinite limit, or the limit may not exist. Okay, but fortunately for this, you can cancel x minus 3 on the top and the bottom, and this becomes 1 over x plus 1. Okay, so this long expression we saw here, which is this expression we saw here, which is this expression we saw here, turns out to be exactly 1 over x plus 1, as long as x is not equal to 3, right? Because I canceled x minus 3. All right, now you can plug this in. X is equal to 3, and you can get 1 over 4 as your answer. All right, so you have many problems. Some of them are challenging. I hope you will practice, and practice. Okay, now I'm not done with 2.3 yet. There's a second segment which I will have to go over some of the other limits and an important theorem called the squeeze theorem. So hang on, and I'll come back and we will do part 2 of section 2.3.